This is GMAT 41. You're welcome to our statistics class. In this video, we are going to look at the topic measures of dispersion. Previously, we had treated measures of central tendencies, measure of position. We now want to look at measures of dispersion, also known as measures of spread. This measure is very important to study in statistics because it helps us to know how the distribution are scattered about on either side of the distribution. Let's have the variables in a particular distribution, how those variables are spread on either side of the center. All right, measures of spread or measures of dispersion gives us information about this. You would recall when we treated measures of central tendency, it was stated that these measures, mean, mode, median, they specifically focus on what? The center of the distribution. It therefore means that they don't take into account other variables that are on the left or on the right of the distribution, that is on either side of the center. They don't focus on them. Then you come to measures of position, it points to a particular variable, the position of that variable in the distribution. Now, measures of dispersion goals are here to tell us about how these variables are distributed on either side of the center, and that becomes very important to study. When talking about measures of dispersion, we have the following of them: the range, the interpercentile range, the quartile deviation, the mean deviation, variance, standard deviation, and coefficient of variation. So we're going to study these measures of dispersion one after the other. We start first by talking about the range. And the range is the simplest measure of spread. It's the simplest measure of dispersion. What is the range? It's simply the difference between the highest value in the distribution and the lowest value in the what? Distribution. So let's assume that we represent the highest value in the distribution by x maximum. That is maximum value. Alright, and then the lowest as x minimum. Therefore, range is equal to x maximum minus x what? Minimum. X here represents the variables in the distribution. So if you have something like maybe 10, 15, 20, 25, 30, 35, 100, is that okay? The highest value there is 100, the least is 10. So that range is going to be 100 minus what? 10, giving us 90. Range as a measure of dispersion is widely used for control of the average quality of manufactured products. That's what it's widely used for. Is that okay? And we may have a chart for range that can be used for the study as per taking note of certain production. Let us assume that maybe in the production process, a machine gives an output that is very large. Is that okay? And then you want to make sure that such quantity is maintained, that it is constant. All we can do is, okay, out of the large output production, we can choose, all right, let's say 4 to 5 items at all intervals, let's say every 30 minutes, and then check their range. Do that to be certain that the variation, maybe the range you got in the first 30 minutes production, is not quite different from the range you got in the next 30 minutes, and like that. So you can set up a range chart. It helps us to determine the average quality of manufactured what? Products. However, range has its limitation. Is that okay? It has what? It's a limitation, and it's very important for us to know that, okay? The limitation of range is that it only considers the least and the highest value in the distribution. It does not take into account all the variables as given in that distribution, and that is a limitation. Why? Because it does not show the clustering of the items relative to the center. And range will tend to increase as the sample size increases. Let's assume that in the first case you got the range like 100 minus 10, which is 90. Let's assume now that you keep producing as the sample size is increasing, and maybe you have something like 200. You're not going to get 200 minus 10, giving you 190. You see a large difference, right? So that is a limitation of what? Range. In the next videos, we're going to look at other measures of dispersion, the interpercentile range, quartile deviation, and the rest of them. In this video, we now consider other measures of dispersion. We have the interpercentile range and the quartile deviation, also known as the semi-interquartile range. Now, the interpercentile range is a measure of dispersion that is based on percentile. Is that okay? You will recall under measures of position, it was stated why these measures are important to study. That is measures of position, where we talked about the quartile, the decile, the percentile. It was stated that some measures of dispersion are based on these measures of position. Of course, you can see that here. The interpercentile range is based on the 10th percentile as well as the 90th percentile. In fact, it happens to be the difference between these two percentiles. Is that okay? And then the 10th percentile and the 9th percentile finds their application in educational statistics. That's where we apply them, right? In educational what? Statistics. It's used for educational measurements. One good thing about the interpercentile range is that it is not affected by extreme values, unlike range is affected, okay? For range, it's usually deal with the highest and the lowest value in the distribution, but interpercentile range is not affected by that. At least interpercentile range is able to take into consideration all values from the 10th percentile to the 90th percentile. A good one anyway. However, it is also limited by the fact that it does not take into account the lowest and highest 10% of the items. Talking about from the 1st percentile to the 9th or 10th percentile, and then from the 91st percentile to the 99th percentile, interpercentile range does not take into consideration those values, and that happens to be a limitation of interpercentile range. Now, more modification. We will consider the quartile deviation or semi-interquartile range. And this range is based on quartile, under measures of what? Position. In fact, the interquartile, that is the semi-interquartile range, also known as quartile deviation, is the average of the difference between the third quartile and the first quartile. We have the formula here that quartile deviation is equal to Q3, which is the third or upper quartile, minus Q1, which is the first or lower quartile, divided by what? 2. Now, the greater the quartile deviation, as the greater the value you obtain here, the more the dispersion or spread of the item. Well, interestingly, this quartile deviation also has its own limitation, alright? Because it does not take into account distributions that are below the first quartile and distributions that are above the third quartile. It does not take into consideration those values, which means something is still lacking. And you know what? A good measure of dispersion should be the one that takes into consideration all the values in the distribution. A good measure of dispersion should be one that is affected minimally, that's very small, by the variation of the samples in the given distribution, which means it's very important to still modify these measures of dispersion. It's important to introduce other measures of dispersion that will take into consideration all the variables in the given distribution. And that is where we have other forms of measures of dispersion. Other forms like the mean deviation and the coefficient of variation. And that is what we are going to deal with in the next video. We'll talk about mean deviation, standard deviation, and of course the coefficient of variation. But mean deviation and standard deviation are the most important. In the next video, we shall consider that. In this video, we have this question on the board we want to look at. Okay, suppose the weekly earning of 6 workers in a factory are 34 naira, 55 naira, 33 naira, 20 naira, 19 naira, and 94 naira. What is the range of the weekly earning of the workers? So we have to look for the range of the weekly earning of the workers. Of course, we know that range, all right, we have the formula to be equal to the maximum value in the distribution minus the minimum value in the distribution. If we look at this weekly earning of the workers in this factory, the distribution shows that 94 is the maximum earning, right? So that X max is equal to 94 naira, and then the minimum earning there, which is X min, that's X minimum is equal to, let's look at that. Okay, you would see that it's 19 naira, right? So we're going to write 19 naira. So we'll substitute into this formula to get our range. It implies that range is equal to 94 naira minus 19 naira. And then 94 minus 19 will give us what? Alright, so we're going to get 75 naira. We're going to get 75 naira as the range of the weekly earnings of the workers. So this is how simple we obtain the range for a given distribution. In this video, we have this question to solve and obtain the interpercentile range and semi-interquartile range. And the question is actually based on table 2A, which shows the scores of randomly selected students in the statistic examination. So we have to determine the interpercentile range and semi-interquartile range. Take note that semi-interquartile range is still the same as what? Quartile deviation. Now, how do we solve this problem? For the first part of the question, the interpercentile range is given as P9010, right? And we already established the formula to be the 90th percentile minus the 10th percentile. But you would recall that under measures of position, we already obtained the value of P90 and P10 for this particular table, right? So the way we actually got the 90th percentile and 10th percentile under measures of position for this table, you have to follow that process, all right? If you've not actually gotten their values, you have to follow that process, get their values, and then substitute. Interestingly, we've already obtained the values, so I will just pick the values. But P90, we already obtained under measures of position from our previous videos. You can watch that, all right? Okay, you can visit our YouTube channel, James41, and then view that to find out how we calculated their values. P90 was actually 82%. and then P10 was 56%. So that the interpercentile range P90-10 will now be equal to P90, which is 82%, minus P10, which is 56%. If you do that, P90-10 will be equal to 82 minus 56 will give us 26%. So this is our interpercentile range. We now have to move on to calculate our semi-interquartile range, also known as quartile deviation. In the previous video, we established the formula to be the upper quartile minus the lower quartile divided by 2. This is simply the average of the difference between the third quartile and the first quartile. Once again, under measures of position in our previous videos, we already established the value of Q3 and Q1 for this particular table, alright? And the value for Q3 we obtained was 75.13%. We got Q1 to be equal to 61.53%. Okay, so our quartile deviation will be equal to Q3 is 75, we substitute 0.13 minus Q1 is 61.53 divided by 2. And then the quartile deviation, if you work on this, should give us 75.13 minus 61.53. Alright, giving us 13.6 divided by 2, that is 6.8%. So this is how we obtain our interpercentile range and the semi-interquartile range. In this video, we consider another measure of dispersion, which takes into consideration as much as possible all the variables in the given distribution. And of course, such measure of dispersion is one that is good, because unlike the interquartile range in the interpercentile range and the range, which simply take into account some values and leave others, this one, mean deviation, try as much as possible to consider every other variable in the distribution. Alright, now I want to start by first looking at the definition of the mean deviation, which is also called the average deviation. Alright, it is defined as the arithmetic mean of the sum of the absolute values of the deviation from the mean. Alright, practically this definition makes more sense if you look at the formula of mean deviation. So quickly, let us look at the formula and see how we define mean deviation from the formula. Are you there? So we go. Mean deviation is defined as the arithmetic mean. Yes, arithmetic mean because we divided everything by the number of what? Observation, which gives us a mean concept, right? An arithmetic mean concept. So it is defined as the arithmetic mean of the sum. This sigma represents sum, is that not so? Of the absolute value. The absolute, there is the slash sign. That slash sign there means absolute. Of the absolute values of the deviation from the mean. This d by I represent deviation from the mean. So simply put, the arithmetic mean of the sum of the absolute values of the deviation from the mean gives us our mean deviation. Of course, this d by I is given as xi minus what? X bar, where xi simply represents the variate value. That is the value of the variables given you in the word distribution. What is the implication of this slash sign used here? It's actually an absolute value sign, magnitude value sign, alright? Telling us if you're doing this subtraction here, xi minus x bar, even if it gives you minus, you have to neglect the minus and use the absolute value of it, which will be positive. Imagine you do a subtraction, you have minus 5. That minus 5, you're taking its absolute value will become plus 5. Is that okay? Fine. Now, so we have the mean deviation both for ungrouped data as well as for grouped data. But first, we start with ungrouped data. In a case where there is no frequency, and in a case where there is frequency. We have the equation number 4 here, right? Which gives us the mean deviation for ungrouped data in a case where the distribution does not have what? Frequencies. And that's the formula, summation of the absolute value of xi minus x bar, where x bar represents the mean, divided by what? Number of observation. The meaning of all of these terms as used are defined here. Importantly, it's very, very useful to know how to calculate our x bar here, that is the mean. Is that okay? To obtain the mean, previously under measures of central tendency, measures of location, we had already treated how to get the mean for this case. And look at the formula is equal to summation of all xi's divided by what? Number of observation. Reason, because there is no frequency here. Is that okay? In this case of this formula. Xi represents the variate value. We now want to consider the formula of mean deviation when the distribution bears frequencies. Is that okay? The formula is given as this. So mean deviation is equal to summation of the product, that is the multiplication of the absolute value of the deviation and the frequency of the varied values. So simply after you do your deviation, take the absolute value, then multiply by what? Frequency, and then sum everything. When you're done with that, you divide by what? Summation of frequencies. So you see in this case, the denominator is no longer number of observation, but summation of frequencies in this case. And then the numerator has to be multiplied by what? By the frequencies, because the distribution came with what? Frequency. You need to consider the weighted mean. Alright, having said that, how do you determine the mean when you're talking about this mean that the values deviated from, how do you obtain it? In this case, where there is frequency. So you can see the formula. Once again, we've made this under mean when we discussed it under measures of location. It is summation xi times fi divided by what? Summation f. Once again, this xi represents the variance value. I am emphasizing on this here because when we're going to treat the mean deviation for grouped data, you would notice that the xi there changes to something else, which is class mark or class midpoint, no longer varied value. Is that okay? So it's very important that you take note of this. In the next video, we are going to consider the standard deviation, after which we talk about equations of variation, and then we'll be set for calculations using this formula established already. In our previous video, we discussed the mean deviation for ungrouped frequency distribution. We looked at two cases there, when this distribution does not bear frequency and when the distribution bears frequency. It was stated clearly that the variance value there, xi, represents the variables, their values as given to us in the distribution directly. The two formulas were established in that case. In this video, we now want to look at mean deviation for grouped frequency distribution. Of course, we'll talk about the variance in an introduction to standard deviation. On the board here, we have the mean deviation for grouped data. The formula happens to be the same as the formula for calculating the mean deviation for ungrouped data that bears frequencies. All right. Now you can see the formula there, that mean deviation is equal to the summation of the absolute value of the deviation from the mean, and then multiplied by the frequencies, divided by sum of all the frequencies. The formula can still be extended to this, which is our di represents xi minus x bar, where x bar is the mean. So xi minus x bar is the deviation from the mean, multiplied by the frequencies of the variables given to us, and then divide by sum of the frequencies. So this formula you see is the same with that of equation 5, okay, for calculating mean deviation of ungrouped frequency distribution when the distribution bear frequencies. The only difference now is the xi. The xi are seen in this formula, alright? The xi in the case of calculating mean deviation for grouped frequency distribution is the class mark. That is the class midpoint. Is that okay? But you would recall when we treated these for ungrouped data, xi simply represents the variance value. But in this case for grouped data, xi represents what? The class midpoint or the class mark. Please take note that for grouped frequency distribution, there must be frequencies. Alright, now this takes us to standard deviation and variance. But first we start by defining the variance. The variance is related to the standard deviation. What is the variance? We have the definition here on the board. We can use x squared or this symbol, alright, squared for it. Now, by definition, it is defined as the average of the sum of the squared deviations of the items from the mean. Does that make sense? We take it again. The average of the sum of the squared deviations of the items from the what? From the mean. We can also see that the standard deviation is simply the square root of what? The variance. Which means that the standard deviation will be defined as the square root of the average of the sum of the squares of the deviation from the mean. We have the definition here on the board as well too. Okay, so this is definition of standard deviation, and of course here we have that of variance. We use S or this sign, alright, for standard deviation. Take note that there is no square there again. The reason is simple, that standard deviation is square root of variance. If you take square root of S squared, this will cancel as the case might be. We're going to consider variance for grouped data, standard deviation for grouped data, variance for ungrouped data, and standard deviation for what? Ungrouped data. Now we have for ungrouped data, the variance is given by this formula on the board. That is summation of the squares of the deviation, right, from the mean, divided by the number of observations. That gives us equation 7. This is a case where the ungrouped data do not bear frequencies. What will be the variance of a particular distribution? In the case where the distribution bears what? Frequencies. So we have the equation given by 8 here. The variance in that case will be the sum of the squares of the deviation. Is that okay? Then multiply by the frequencies, divided by sum of the frequencies. Once again, in this case, our xi here represent the variate values. In the next video, we are going to look at the standard deviation for this case, and then consider the variance for grouped data and standard deviation for grouped data. In this video, we now want to look at the standard deviation for a distribution that do not bear frequencies and a distribution that bears frequencies, right? You would recall from our previous video, we established equation 8 and 7. Equation 7 was a case where the distribution does not have frequencies, and of course we defined the variance there. Equation 8 is a case where the distribution has frequencies, that's ungrouped frequency distribution, but it has frequencies. We define variance there. Now what's going to be the standard deviation for these two cases? That is why we have equation 9 and equation 10. Recall that by definition, standard deviation is the square root of the average of the sum of the square of the deviations from what? Their means. Alright, so all we need to do is simply take square root of variance in each case. So you go to equation 7, take its square root, you get standard deviation. Is that okay? For a situation where the ungrouped distribution does not bear frequencies. Then go to equation 8, take the square root. If you take the square root of the variance there, you get standard deviation for a case where the variables bear what? Frequencies. And that's the formula that we have here on the board. Now let us quickly move into grouped data, where the distribution is a group frequency distribution. How do you obtain the variance? How do you obtain the standard deviation? Before going into that, you want to always have in mind that for group frequency distribution, there must be what? Frequencies, alright? So this is the formula. The formula happens to be equal or the same with the formula for ungrouped frequency distribution that bear what? Frequencies. Does that make sense? The only difference now is how you, what your xi represents there. Is that okay? What your xi represents. So look at the formula. For group delta, the variance, alright, you can see it here. Summation xi minus x power all squared times fi divided by summation fi. Then the standard deviation is to take square roots of the variance. So you have this. Now the difference between a case of ungrouped data and a case of group data is the xi, like I said. Just like we encountered under mean deviation, it was stated that the xi for ungrouped frequency distribution is simply the variate values as given from the distribution directly. But for grouped frequency distribution, the xi represent your what? Class marks. Don't forget that. Please, you can make a note of this. Get your pen, get your book, and write. You see this formula built for standard deviation and for variance. There are cases where the denominator is what? N. There are also cases where the denominator is summation f. A distribution can be referred to, or a sample can be referred to as small sample. Other samples can be referred to as large sample. Now, you take note of this. If you are dealing with small sample, alright? Small sample is one in which the number of observation, n, is less than 30. Is that okay? In that case, we represent this n with n minus 1, alright? And then summation f, we represent it with summation f minus 1. Although, even if you do that, the differences in the results as compared to when you use n and summation f directly will just be minimal. Is that okay? Very insignificant anyway. And then for large samples, large sample is a distribution in which the sample size is greater than or equal to 30. That is to say, n is greater than or equal to 30. We refer to such sample as what? A large sample. In such case, that is why we use this over n and over summation f directly. Now, we want to look at the last measure of dispersion, which is coefficient of variation or coefficient of variance. Why do we actually need this? We use it to compare the standard deviation of two or more different sets of values. You know, standard deviation, the unit is always the unit given to the distribution you're dealing with. So just imagine that a particular distribution, the unit, what you are treating there is about naira, and then another one where you are treating them maybe is about weight, and then they are expressed in kilogram. Imagine you calculate the standard deviation of a distribution whose unit is in naira. The standard deviation will be obtained in the unit of naira. And then you have another distribution whose unit is kilogram perhaps. The standard deviation for that distribution is going to be in kilogram. Now just imagine you're asked to compare these two standard deviations. How can you do that? Of course, you cannot be talking about something in naira and something in kilogram you want to compare. They are of different units. So it's going to affect your comparison. In order to obtain a correct comparison, what do? You need to find a common base for them. Convert them to the same unit before you can convert. You can compare. And that is why we have our coefficient of what? Variance. It helps us to compare the standard deviation of two or more different sets of what? Variables. And what does it do? Simply convert the standard deviation in any unit to what? To percentage. And look at the formula. Coefficient of variance is equal to standard deviation S divided by what? The mean times 100. In the next video, we are going to look at the relationship between standard deviation and mean deviation. And then we shall pick questions and see how we apply these formulas that we've established so far. Formulas for mean deviation, formulas for variance, formula for standard deviation. Now, before leaving the stage, I want to also quickly state, it's something you need to put down as well too. What is the limitation of mean deviation such that we now introduce standard deviation to measures of dispersion? You would recall that for mean deviation, there was a point you took absolute values, and it was stated that if you do xi minus x bar and you get negative value, simply neglect the negative value because you're taking absolute values of it, right? That is a limitation in itself because it does not follow classical mathematical operations. What usually removes negative from a term in mathematics is when you square that term, when it is raised to an even power, alright? So the conscious negligence of negative sign in that xi minus x bar for mean deviation sets in a limitation. And that is why standard deviation becomes the most important measures of what? Distribution, because it solves that problem. To remove that negative, you notice that the formula is xi minus x bar all squared. If this deviation gives us negative, this power 2 will take care of that negative for us. So you now notice the limitation of mean deviation, which made us introduce standard deviation to measures of what? Dispersion. In this video, we now look at the relationship between the three deviations that we met under measures of dispersion. You would recall, we encountered quartile deviation, QD, we encountered mean deviation, MD, we encountered standard deviation, S. Now there's a relationship between these deviations, which means if you're able to get one of them for a particular distribution, you can use this relationship to get the other ones without using the base formula that we established already, without going through constructing tables all through for each case. Is that okay? Once you really calculate one, you can use the relationship we have on the board here to obtain the other deviations, okay? So the first relationship, we have it here that standard deviation is approximately equal to 1.25 times mean deviation. Of course, this relationship is important for us to know that we apply it when the distribution is fairly normal. Is that okay? In the case where the distribution is fairly normal, you can apply this formula and then you would still be correct. So if I know my mean deviation, I can multiply by 1.25, which is of course 125%. Is that okay, of mean deviation, to get my standard deviation. Then look at this second relationship between quartile deviation and standard deviation. If I know my standard deviation, I can multiply it by 0.6745 and get my quartile deviation. This is 67.45%. Is that okay, of standard deviation? So you see that getting one of the deviations can help us to get the other ones. Now, since we know that there's a relationship between standard deviation and mean deviation, and there's a relationship between quartile deviation and standard deviation, if standard deviation is approximately equal to this value, I can put this value into this equation, which means that there will be a relationship between quartile deviation and what? Mean deviation. And that gives us that quartile deviation is approximately equal to 0.8431 times mean deviation. So it's very important that we take into account these relationships, alright? It's going to help us to be very fast in solving certain questions in a case where we are dealing with time. In the next video, we're going to pick questions and then apply all the formulas we've established for mean deviation, variance, and standard deviations.